All right, so today we're going into section 5.2, which is just another way to continue with our integration. It's called integration by substitution. So, like always, let's do a couple of slides from this PowerPoint, the one that you all should have access to still, and then I'll do a handful of homework examples as well. So, let me show you what we're talking about here. Okay, so little memory here. Remember when we were doing a derivative, our derivative here of some function, and if there was another function inside, remember how that worked is you would do the derivative of the main function, and then you had this chain rule. This is the inside, whether it was a power, a parenthesis, whatnot, a square root, that was our chain rule. So it's kind of the same idea when we're working backwards. Now, I know these letters are not going to be clear, so I'm going to clarify it for you all in a second. But what it's saying is, if you have a function like this, remember, forget what we have here on the right, but if you just have any kind of a function or something, if this is just an x, so let's go with this to make life easier. If I was integrating x to the n, remember the rule is you take x, you add 1 to the power for integrating, and then we divide by that new power and we get our plus c. Okay, so notice it's the same kind of thing. You have something here to the n power, and you still add 1 to the power and you divide by the n plus 1. Okay, the difference is we need to have the chain rule kind of already built into the problem. So that's what we're going to do. And if you remember me saying a few times before, the calc part isn't going to be hard. This power rule, adding 1 and dividing by the new power, is not difficult. What's going to be difficult is the work we do before the integral and what we do afterwards. So a lot of these problems, including this new integration by substitution, there's going to be a lot of preliminary work. And that's what we're going to have to worry about. And that's where your algebra is going to come into play. So let me get over here and, I'll show you the formula. And I just want to get to a problem here. And in all cases, it's pretty much going to be the same thing. These are all things we're used to doing. Just like this last one is like a 1 over x, how that is natural log of the x. It's the same kind of thing. If you have something on the bottom, it's still going to be natural log of that thing on the bottom, but you have to have this derivative in all three cases. Okay, that chain rule is what you need if you were to go backwards. If you were going to take a derivative of anything, like these three answers, you'd have to go backwards and you'd get all of these. So maybe look at it that way. If you were to take the derivative of this, for example, it is the same thing. And then the rule is you multiply by the derivative of whatever that power was. Okay, on the third one, it's kind of the same. If you want to take a derivative of some natural log, it would be 1 over that. And then you'd have to multiply by whatever was in that denominator. So the difference in derivatives is, well, we have a process. We just go find the derivative of that piece. We apply the chain rule. On integrals, it's a little bit different. You have to have the integral already here. Sorry, you have to have the derivative. The chain rule part has to be part of the original problem. Now, in the beginning, you're going to see some problems already have that. And then later on, we're going to have to find a way. We're going to have to invent that and come up with that. So, give you a first example here. This one's already tailor-made, and this is going to be the case, like I said in the first few, but what they want you to see is that, okay, see, this is the complicated function. There's something in there to the third power. But what's nice is this is the derivative already of whatever's here on the inside. So notice if you took the derivative of x to the fifth minus 2, you get a 5x fourth. So because this is the derivative, it's already built in there. Basically, it's just like us going along and saying, this is like, I'll pick a different letter. It's like saying y to the third is all we're integrating. And then you apply those same rules and you get all of that. Okay, that's kind of in a nutshell what it's going to be here. Okay, so on these first few, I got to tell you, they only work because it's perfectly laid out, but they're just pointing out. Now you see how the inside is that f of x. The inside is the part that, usually it's an x, but it's got some more to it. It's got this x fifth minus 2, but it's okay because of this derivative, because this part's over here. Now, I'm going to jump through a couple of these slides just because I don't want you to have to worry. Let me go back. These formulas right here, they're not so important, okay? And I'll tell you why. What's important is you still remember how to integrate with a power, you know how to integrate with an e, and you know how to integrate with a 1 over something. That's all that's going to matter, because for all three, I'm going to show you this process called integration by substitution, and that's going to give us our answers. So in a problem like this one, okay, let me just cut through these. All right, so the substitution is going to work like this. All right, you have to worry about replacing something. You're going to substitute something to essentially make your problem better. But the rule is you have to have the chain rule in play. You have to have that other derivative in there. So I'll show you, get to an actual example here. I'm going to go with just the letters. Like I said, I don't want you to over worry about this f of x, g of x, these things. This tends to kind of make things bad for people. So here's how we're going to do this one. I'm going to go to the one that actually matters here. This problem. So when you recognize this, generally, it's going to be because you have something that's very complicated. Now, let me just point out, this is not the way we're going to do this, but you could actually take this power of 7. So you would have 7 of these parentheses in a row, and then you'd have that 2x plus 2 over here, and you could do a big superfoil super distribution, and you can get probably about 8 terms in the end, and you can integrate each term. But as you can guess, that algebra is going to take a very long time to do. Okay, it'll take a long time to do that. So that's why we're trying to work with some of these shortcuts. But here's how the rule works. When you're going to substitute, you're looking for the piece that's complicated, but something you know how to do. So we have 2 things going on here, and I want you to focus on the more complicated part, the more complicated parenthesis, if you want to call it. It's more complicated because it has this power of 7. That's the thing I'm focusing on. And I'm going to point out that if this was just a plain, say, x to the 7th, you would have no problem integrating that. You know how to integrate that with the basic power rule. So what we're shooting for is we're going to try to turn that into exactly that. The problem is we have that big complicated x squared plus 2x plus 5 inside. We're going to get rid of it, so it's called a u substitution. You replace that entire parenthesis with a u. Just like that right there. So u equals x squared plus 2x plus 5. Okay? So now, the next step of any u substitution, and I'll tell you, you can make u, the letter u, that's what we're going to use every time. It could be anything you want. The idea is that you want to make it something that makes your problem better. So I'll kind of jump down to the bottom. This is what we're eventually going to have. We're replacing that whole parenthesis with a u. But there is one little caveat. You can't just turn your problem into an easy one. You have to now take the derivative. So we take the derivative and we get this 2x plus 2. The derivative of the u, I should clarify that. Okay? Now, this next part is going to seem kind of weird, but we're going to multiply both sides by that dx, and this is what we get. And here's how it works. When you have an x variable and you're integrating, you should have a dx as part of your integration, okay? When you have a u, like in this case, you should have a du. And that's what we need to do. So we're going to replace everything here. They're all going to become an integration with a bunch of u's. I'm just writing some u's in general. And then there needs to be a du. So it's either all x's and a dx, or it's all u's and a du. But that's the substitution that we're doing. That's the replacement we're going to do here. So we've already taken care of that first parenthesis. That's going to become a u. Now we have to worry about all this, but you see how you notice this thing that I'm underlining? It's exactly equal to this right here. So this entire piece becomes a du. Here's what our whole problem becomes. It becomes a u to the 7th du, and now we can integrate normal. Okay, so I know this is kind of brand new for all of you, so pause. I'll go over this again real quick if you need. You let something be u, whatever it is, it doesn't matter, but you must immediately take the derivative like I did right here. And I'll tell you, you don't even need this middle step. You go right down to here. You take the derivative of that, which is du. You take the derivative of x squared plus 2x plus 5, and you get a 2x plus 2 dx. And then you need to make sure that all of this is in your original problem. And now later on, you might ask, well, what happens if it's not there? We'll deal with that in a bit. But right now, that's exactly what it is. So that whole thing here becomes a du, and my new problem is u to the 7th du. And now we integrate with our new rules. And remember, like I said, the calculus is the easy part. That's it right there. Okay, the only problem is we're not quite done. They started the problem with x's. We have to finish the problem with x's. We temporarily went to u's, but now we're going to go back to x's. Okay, so this is why this line right here is very important. We're going to replace u with the thing that we got rid of to start, this u squared plus 2x plus 5. And now we have the answer to the problem. That right there. Okay, so again, pause if you need to check this out. I'll kind of show you the example of how this works here. Think of it as we have a problem. We have a solution. The problem is when we're dealing with x's, the road's out. The road's broken. We can't get there. So what we do is we're going to jump tracks to the u's, do the problem, and then, oops, sorry about that. And then we're just going to jump back and finish the problem as an x. This is kind of our way to get around, there's an obstacle. There's something we can't do. We can't figure it out. So we're going around it. We pick another letter. We rewrite our problem. And that's how we're able to get the answer here. Okay, so check that one out. I'm going to do a lot more of these, so don't worry if it's not 100% clear on the very first example. Let me do another one, and you can just see exactly what I'm talking about here. So I've already done it, but I'm just going to quickly go through the slides so you can kind of see it a little bit neater. This is what they've done. They've done the u, and then they take the derivative, which is du. So it's kind of weird because we're trying to integrate, but part of the process is we have to take a derivative. We take that, we replace all of this with a u, we replace the whole thing here with a du, and now we have u to the 7th du, integrate that, and then re-substitute back. They put the 1/8 that in front, I left it on the bottom, either way is going to be fine, and there's your answer. Okay, so going to go through a couple of things. This is just a reminder of your formulas, whether these are x's or u's, it's going to be the same thing. You have your power rule, add 1 to the power, divide by the new power. E to the u du is just e to the u. 1 over u du is natural log u. So the formulas still work. The process is exactly the same as before. It doesn't matter what the variable is in this case. Okay, so this part, I'll let you pause if you need to see them, and I'm going to keep talking as we do examples and we do the homework so you can see how it works here. They want you to try to look for something to substitute, then see if you can rewrite the entire integrand. Remember, that's the problem, the integral, in terms of u and du. And you have to make sure you can't have any x's lingering behind and everything has to become a u. Then you integrate it, and then you go back to the original variable that you started with. So here's another example we'll look at, and I'll kind of not write this one out. You can just follow along, but it's the same thing. Just like the last problem, you have something semi-complicated to a power of 4, and then you have something kind of easy over here. I look at this as, if this is just an x to the 4th, I know how to do that, but with all this extra terms and extra powers in here, that's what messes me up. So the solution is, let's substitute the base. Let's get rid of this x cubed minus 5, and we'll do that by substituting u in place of that. Notice we're not replacing the entire parenthesis to the 4th, it's just the base that we replace, and then that becomes to the 4th. So this inside is u cubed minus 5. Then remember, your next step is take the derivative of that. Whatever it is you're using for the u, it's your choice, but the derivative you have to follow the rules on. That's a 3x squared, and remember, it's a du equals 3x squared dx. And like last time, notice this 3x squared dx exactly matches what we have in the original problem. Okay, exactly the same. So now that's an x cubed minus 5. That becomes a u. This whole thing becomes a du. And now our problem becomes integral of u to the 4th du. Integrate that. We have u to the 5th over 5. And now we replace, replace this u with the original substitution. So that's why it's important to write this step here. U equals x to the 3rd minus 5. It's like a temporary substitution. So when you get a final answer, you can't end it with a u. You have to put that x cubed minus 5 back in there, and now you have your solution. And also, I'll remind you, don't forget that plus c. Important every time. Okay, so I'll pause right here again for a second. If anybody needs to, pause your video, I should say, and then I'll continue on here. All right, so we're going to do the same thing here. Now notice, we got a weird power here. It doesn't matter. The whole goal is let's get that power. Doesn't matter if that's a 5, a 7, a 1/2, anything. We're going to replace the base to make it something we know how to integrate. So when in doubt, take whatever's in the parenthesis to that power, and that's what you're going to replace with u. So u equals x squared plus 5, du equals 2x and dx, and that exactly is what you had here on the second half. So we now rewrite this as integral of u to the 1/2 du, and follow your rules. Same integration before. Add 1 to the power, gives it a 3/2. Divide by the new power, so we have a 3/2 down here. And then just remember, we've done this a few times, when you have a, when you have a fraction on the bottom right here, it's like multiplying by the reciprocal, 2/3. So you don't have to deal with that little fraction on the bottom of a fraction, all that. And then last step, resubstitute back. This u, this is our answer, 2/3 u to the 3/2, but get rid of the u because you can't finish in u's because that was our variable. We're going to replace it with the original variable, x squared minus 5, and there's your answer. And again, I'll keep reminding you of the c. Hopefully I don't forget them, and hopefully you don't forget them when you're entering your homework answers tonight on the homework, sorry. So now we have another one. Same kind of thing. Now this is going to change it up a little bit, but just kind of follow the steps. I want to let u equal to this base because I'm looking ahead. I'm thinking, if this is u to the 4th, I know how to do this problem. But when it's x cubed minus 5 to the 4th, I can't do the problem. So I let u be equal to x cubed minus 5. du is 3x squared. Now notice the first problem is we have, I kind of write down what we have, and I'm going to write this a little bit larger over here on the right. Here's my problem. So when we do our replacements, this is going to become a u. The problem is over here, we don't have the exact same thing like we've been having. We've had that luck where whatever our du was exactly the same as here. Notice I have the x square, but I don't have the 3. Well, there's a simple solution to that. You can put a 3 right there. Okay, now I know some of you are wondering, well, how can you get away with that? You can't just put it there. I can multiply my problem by 3 as long as I multiply it also by a 1/3. So notice the things in green that I did. I brought a 3 and I brought a 1/3. That's basically like multiplying by 1. So I haven't changed the value of the problem, but I can do that. So if ever the numerical part doesn't match, it's an easy fix. Just put the number that's supposed to be there and then divide by that number, or in this case, multiply by the reciprocal, and then you're going to be okay. All right, so that's what I did. So notice the stuff in green is the part I just added now. That's okay. And now it's looking just like this. So that's going to be the u, that's going to be the du, and our 1/3 is still there. So this is what we are going to have. And you'll see on the next line, if I can get that, there it is. So they talk about that same thing where we got to get that 3 there. So they put the 3, they put the 1/3, just like I said. And now we have 1/3 u to the 4th du. Okay, so that's the quick fix. If this does not exactly match your du, which is going to be the case more often than not. Okay, our first problems, we were just kind of spoiled and lucky on those. But now that's going to be the case where this was not exactly 3x squared. Oh, it's okay, I can put the number in there, then compensate by multiplying the front by a fraction. And notice that front number doesn't affect anything. All it does is just stick around to the end. We still do the variable part the same. And what do we get here? We get a u5 over 5. That 3 lingers around, so that's like a 15. And then once again, like always, replace the u with the original substitution, which is x to the 3rd minus 5. Okay? All right, now we can do the same thing again here. We're getting more complicated things, and you're going to see most of the time this integration by substitution, or what you might hear instructors call it u substitution, is usually when you have multiple things here. So I'll point out, when we were doing the derivative and I had two things multiplying to each other, we had the product rule, we had the quotient rule, we had the chain rule. Unfortunately, none of those things work in integration when you're going backwards, okay? The closest we have is this u substitution, which is sort of like a backwards chain rule, but it's not exactly that easy. So we have to follow that process. Now you have two options here. You can let u equal this, but that doesn't help so much because the base is already a nice x. Whereas over here, this e to the 4x to the third, that's all the power. I don't want that complicated power. I want to make that power something basic. So that's going to be my u substitution. I'm going to replace that power with a 4x to the third. Now, once again, as soon as you get the u, du is your derivative. It's a 12x squared dx, and that's what we need. So notice there's going to be a little rearranging. There's no 12 in there. So they didn't write that, but I'll kind of show you what I would do just because sometimes this helps people visualize this a little bit better in the beginning. This problem is exactly the same as if you have this. Okay, so they're just two things multiplying together. It doesn't matter if the x squared is first or the e is first. They are both multiplying, so they're both good. Generally, you just put the x's first and the e always goes at the end. But for our purposes of trying to do the u substitution, this helps because now, just like that last problem, I need that 12. Okay, there's no 12 in there, so what do? I can put that 12 and I'll kind of squeeze it there as long as I put the 1/12. And now I have everything here as my du. And then that's going to become an eu, as you see on our next step right here. Maybe, there it is. 1/12 e to the u du. Now we integrate that. Remember, this is the easy part. The integral of eu du is just eu, just like that. All the work is this stuff up ahead. It's not going to be the integration. Believe me on that. All the work's going to be here, and then later on, you're going to get a bunch of work after here. This one step, the one thing that's calculus, is the easiest part of your problem pretty soon. You're going to see that. Okay, so it's all about making it clear, trying to set it up, trying to make it look to fit the right form. Then you do your quote-unquote easy integration, and then you just clean it up a little bit at the end. Okay, so we have that 1/12 e to the u. Don't forget. Don't finish your problems as a u. Replace that again with the original u, which is again why this line right here is so vital. Because after you do all this work, you're going to wonder, what was my u again? Oh, you got it written down. It's not a matter of backtracking. It's right there, plain and simple. The power becomes 4x to the third, and there's our answer right there at the bottom. Now, once again, even though you're doing all these complicated steps, you still have to have the ending plus c. Okay? All right, now we'll do another one. And again, it's the same kind of thing. We have to try to backtrack and try to think, well, what's going to make this problem better? Well, this x on top is not bothering anybody. It's an easy x is what I call it. What's complicated is all this stuff on the bottom. Okay, so I'll kind of jump ahead. If I had this, that's a problem we know how to do. Okay, but I don't because I have all that stuff inside. So generally when you're doing a u substitution, you're looking for a complicated denominator, a complicated parenthesis, a complicated root, something that's more than just a simple x. That's what you're going to replace. So you'll see here, we're going to use a u substitution of 5 minus 2x squared. Immediately take your derivative. As soon as you get the u, go get your derivative. Negative 4x dx. Okay, now you look at what's going on here on our problem. Du has a factor of negative 4 that's not in the integrand. Okay, and what they're saying is, that means we got to fix that. As long as the x power and all that stuff works, there's not going to be an issue because you can fix the numbers. So that's what we're doing right here, just fixing the numbers on this one. And we have the x up here on top because it's already x times dx. It's the negative 4 we don't have. So how do we do it? We take the negative 4 and where is it at? I know it's not in blue this time, but here's the original problem. I need a negative 4 dx. Now remember, when you have a fraction, dx is like it's on the top. So right here, it's like an x dx. We need the negative 4, so we shove the negative 4 in there, and we balance it by putting a negative 1/4 out front. So those together, like I said, is like a positive 1. Doesn't change the problem. So we have that. We get a negative 1/4, negative 4x dx. All over all this. This entire top becomes a du, and we get this. And in case you don't like this, and I've never really done it this way, but it's the same thing, just realize that this is the same. whether it's a du over u fifth or it's a u fifth or 1 over u fifth du, they're the same thing. Either way, you have to rewrite that as a, they didn't write this step, so let's go back. We're going to write this. You have to make this what you guys know. This is a negative 1/4 u to the negative 5 du. We've done these before, just don't forget them. You know, easy to forget them because you haven't dealt with them. So that's the same as this right here. When it's a u on the bottom, it's like a power of u to the negative 5. And now we can add 1 to the power, which becomes a negative 4. Remember, you're adding 1 to the negative 5, which is a negative 4. And then we divide this by negative 4. And that's how they get that problem right there, that answer right there on the bottom. And then, of course, the negative 1/4 and the negative 1/4 becomes a positive 1/16. And then they put the u back down on the bottom and replace the u with the original substitution. Okay, like I kind of drew on that first example, you're just taking the problem, you're switching tracks just to do it, and then you switch back. Always make sure you switch back. Okay? And now we get another one of these. So you're going to see that the best way to learn these is literally by doing more and more examples. All right, on this one, we're going to replace this right here. This power that's, anything higher than a 2 is usually something you want to substitute down. So it becomes an x plus 6. That's my u. And you get this sometimes where, well, du is just 1, so du equals dx. And that's kind of nice because you don't have to worry about compensating. You don't have to worry about fixing anything. You just have to go and swap the 2 out. So in this case here, the x plus 6 becomes a u, the dx becomes a du. So we're good, except there's a problem, and there's an x still hanging out right here. Okay, remember what I said earlier? You have to wipe all the x's out, and unfortunately, we've had it where this is taken care of with a du, but in this case, it didn't, so we have to figure something out, and it's an easy fix. See this original u substitution? If I have an x that I want to get rid of, I can solve that for x. All it takes is just moving this 6 over. So x equals u minus 6. And I replace the x, this one lingering x, with the u minus 6. Okay, now a lot of you are going to look at this problem. Okay, now we have only u's. If you look at these two, it doesn't look like you did much better. Okay, I'll point out why it is. This is our new problem with u's. This is our original problem with x's. It looks like we just slid stuff around. And you're right, except for one important fact. The 8 here is just on a single letter, a single term. Here it was on 2 terms. This would have been horrendous to write out 8 times. We don't want to go there, hence we're doing this one. This one, though, isn't so bad because, we can just distribute this. It's a single term. We distribute the u8 to each term, and we get a u9th minus 6u to the 8th. Instead of all these multiple terms up top, it's one term distributing, and it's power of 1 for the u minus 6. So we just get 2 terms. It's a little more complicated, but it's not as bad. These are both things you know how to integrate. Remember, this is u to the 10th over 10. This is u to the 9th over 9. There's a negative 6 right there. And all we have to do is substitute back, replace u with the x plus 6, replace that u with an x plus 6, and we are pretty much done. That's it on this problem. Okay, so again, give you a chance to check that over. Pause the video if you need to get a better look at it. And then we'll go on to the next one here. And you might have seen this is going to be one of our little bit of a word problem. Nothing we can't do. Company finds a marginal price, P prime of X. Remember, the derivative is the marginal price. So if X bottles of baby shampoo per week is given by this formula. So the question is, they want to get the price supply equation. Now in English, here's what they want you to do. They want you to find the derivative of, the integral of this. And once you find the integral, just then you have a regular function. That's what they're trying to find, is what's the original function? We already have the derivative. Let's go backwards. Okay, so, and they tell you this other fact. We'll get to that in a second. So to get P of X, they tell you that P of 75 is 160. So the second part right here, they're telling you if you have 75 bottles, the price is going to be $1.60. That's going to be important for the second half of this. Okay, so we're going to come back. Main thing, to get the p, we want to find the integral of this equation they gave us, this one right here. Now we know how to do it. We do a u substitution for that piece. So I'll start over right here. Let u be that complicated formula, 3x plus 25, then du equals 3 dx. So we have to do some modifying here. Now notice, we need a 3 dx, we have a 300 dx. Couple ways to do that. They may not have shown it, but this up here is exactly the same as saying 100 times 3. So when you need a 3 dx, well, we've got it. We just had to kind of find it a little bit. We pulled the 3 out of the 100, and then the 100 lingers. So that's what happened right here on their example. They pulled the 100 out, but they left the 3 with the dx. That becomes the du. And then, of course, that entire parenthesis on the bottom becomes a 1 over u, or that whole bottom becomes a u square. All right? So now we get a derivative of this, and they didn't show this, but remember I did this last problem. This is like 100 u to the negative 2 du. And when you add 1 to that power, it becomes u to the negative 1 over negative 1. That's how they had this problem right here, this negative 100 over u. So like I said, they don't always show it every step. That's why I want to supplement and give you a little bit more. Last part, of course, put the new u. Now we have this. Now remember, this is the formula, but this c could be anything. The c could be 0, it could be 100, it could be 300. We don't know what this is. That's the problem when you do integrals is we're missing. We're unsure what that is. That comes back to that original piece of information they gave us earlier. So we're going to take this, what they call the general equation. This is the function, but we got to get rid of the c. We have to figure out what that c is. So remember this one fact? They told you that when the shampoo bottles was $75, the price is $1.60. Based on that fact, I'm going to replace all of this stuff in this new equation we found. Okay? The x, replace that with 75, and then the whole function equals $1.60. So this is all this stuff on the right. And we clean this up, and we solve for c, and we find that c equals 2. What that means is now I can rewrite the equation p of x. Instead of this plus c, I found the c is 2. This is my function right here. This is the answer. Okay, and I think this, and that was all they're asking, I think. Yeah, they just want how to get that, the actual equation. So this is what you get when you found the integral. And if they tell you one important fact about the original equation, like some connection, like an xy, in this case, a p and an x, you can use those to replace and then solve for that c, and that's how you can get the answer right there. Okay? So that's what we get. And now let's get to some problems, because like always, this is probably, the problems is what matters to most of you. So I'm sure some of you might have even fast forwarded to this. That's fine. Let's get to the problems here. So assignments, there we go. This week, as you see, we have 5.2 and 5.3. So let me pull these up, and like always, I'm going to do every 4 of them, starting with number 3, and see what we get. Okay, so starting with number 3 here, let me make this a little bit larger. Okay, so they want us to find f prime of x. So notice this is not an integral. These first couple problems are sort of integration or reminders of the derivatives, because as you saw, we're using so many derivatives here. We have to know how to find the derivative of a given function. And they want it to be where it's kind of a faster process. So f of x equals 3 natural log of 1 plus 3x squared. Remember the rule. When we find the derivative of this, it's going to be a 3 still, and then the natural log, the derivative of that is just 1 over all this. But we have the chain rule, which says I need to multiply by the derivative of whatever that is. That's the chain. The derivative of the inside. So the only thing you have to do is pretty much clean this up a little bit and get this as your derivative. Okay, so just a quick reminder that that's what these first few problems are, is just to kind of get you used to all this stuff here. So this should be, and of course, if you can simplify, please do, because sometimes that's going to be necessary. Generally, it's not. It depends on the problem. This one can't be simplified, so I think we have everything right. And remember, this is derivatives. There is no plus c. That's for integration. Okay, that's what we have here. So again, check that over if you need, and we'll go on to the next few problems, doing the same kind of thing here. All right, let's look at number 7. Okay, so number 7, we have e to the 12x times 12 dx. And in this particular case, I'm going to go through this. You're going to see pretty much the same procedure each time from me. All right, e to the 12x, 12 dx. Sorry, that was bad writing. But I'm kind of looking ahead of, I would love it if it looked like that, because I know how to find that integral. So that's the kind of a jumping ahead of, you want to look at it as, I'm trying to, what's my goal? What's going to make it look nicer here for me? And that's what it is. Okay, so how do I get there? U equals 12x. And immediately remember, take the derivative of that, which is 12 dx. And it just so happens, we're lucky, that's exactly what is there. So I have e to the u du. And now I can integrate this. Well, the integral of e to the u du is e to the u. And forget the plus c. Last step, replace the u with what we had originally right there, and you have your answer. So let's see what we get here. E to the 12x plus c. And again, I should have done one without the plus c. Just to remind you, if you don't put the plus c, you are going to get marked wrong on almost all of these here. All right? And that's it for that one. So same thing as always. Go ahead and pause if you need a little more time. And when you're ready, unpause and move forward. Okay, let's look at number 11 here. Now, I hate giving these when there's S's, because these do look like 5s for some people. So I'm going to try to make it very clear, and hopefully I don't make that mistake. So we have an S to the 3rd plus 3 to the 5th power, and there's an S square here, and we're going ds. All right? So same thing. I'm looking at what's complicated. I see that power of 5, and it doesn't have a nice inside. So what do I do here? I have to try to get rid of that. I'd like to get rid of that whole inside, so that's going to be my u. Now, some of you might be wondering, well, where do you write the u? Generally, I'll do it right off to the side. Okay, and I'll do the du there. I'll do the du right underneath it. 3s squared ds. And then I'll try to put everything into the problem. So like always, the most important thing is the du, okay? U can be anything it is, that doesn't matter, but it's what you do with the derivative of it. Do you have the derivative ready? So I need a 3s ds to proceed. Well, 3s squared ds. I have the s squared, got to put that 3 there, and remember the compensation is I'll put a 1/3 right there, okay? So now, excuse me, let's do all the substitutions. This whole parenthesis becomes a u, so I have u to the 5th. Power doesn't change. And all of this becomes the du. So now I integrate, and that's u to the 6th over 6 plus c. That becomes a 1 over 18 u to the 6th. And of course, your final part, make sure you resubstitute back, because if this problem began as an S, you need to give the final answer as an S. So, oh, this one's good. It's even a multiple choice. So they're asking, I'm sorry, there's 2 parts. They want you to actually figure out what's the appropriate substitution. So out of all these choices, remember, you don't want to make it too complicated. You don't want to make it too basic. That right there was the u that I used, this s plus 3. So I'm going to pick that. And we should be good. And then part 2 is find the indefinite integral. So luckily we didn't do all that work for nothing over here. We have an s to the 3rd plus 3 to the 6th end your parenthesis first. So let's see that again. And that whole thing is over 18. And I'll do it again. I won't put the C just to see that it'll get marked wrong. And this is the first thing I want you guys to point out. I want to point out to you all. If you get it wrong, don't panic and do the whole problem over. First thing, check. Did I forget the plus C? Now, if we get it wrong, now I'm going to not panic, but I'll just have to do some more things. But we got it right. Okay, so look that over. Pause it. When you're ready, unpause it. Let's move on. Let's look at number 15 here. Okay, so on this one, follow the same steps every time. I'm looking at where I can make life better. All right, I don't have a parenthesis. If I had a root, a parenthesis, I would replace that whole thing with a U. If I have a denominator that's complicated, I'm probably going to replace that with a U. Now, I won't say that's the rule every single time because there's always going to be an exception and there's going to be some of these quirky problems we're going to deal with later on. But for now, I think let's let that whole denominator be the U. And you're going to know pretty quick when you take the derivative and you get this du, if it's a problem or not, if you're on the right track. So that's kind of your benchmark. Did I pick the right u? Did I do this right? Well, the main test is look at the du and see if you're in business or if you're making the problem worse. So in order to make this get a du, I need an 8x to the third dx. Well, I have the x to the third. That's the part that should be looking good to you. I just need an 8. So I'll put the 8 there. And remember, you put the 1/3 as a balance. So now we get 1/8. The entire top becomes the du. And the entire bottom becomes the u. So we have 1/u du. All right? Excuse me. And now we integrate it. 1a stays there, and the rule for integrating that is, let me write that a little bit neater, the natural log of the absolute value of u plus c. So our last part is replacing that, and remember, you always replace it with the original x that you had. Let me get that right here. That's going to be our answer. And remember the absolute value symbol's right there. 1 plus 2x to the 4th. And make sure the c is on the outside. All right. And another thing, so while you're pausing and checking this out, one thing you can always do, it's going to take a little while, but if this is an exam, you can always take the derivative of this answer. Okay. The c doesn't matter on the derivative. Excuse me. The derivative of natural log is going to be 1/1 plus 2x to the 4th. Then times the derivative of this, which is 8x, the 8's will cancel, and you notice, or 8x third, I'm sorry, and you'll end up with the same original problem. So it's always a way you could check your answers, especially if it's an exam. You know, on this homework, they'll tell you if you're doing it wrong, but on an exam, you get one shot on your quiz. Next Monday, you get one crack at this. Why not go, excuse me, and take your derivative if you have time? Maybe, you know, my suggestion might be is do the 8 or 10 problems, whatever you have on the quiz. Just do them, enter these answers, and then if you have time, go to the ones that seem troublesome to you, work out the derivative off to the side, see if you get this original problem. If you do, you know that one's good. You don't have to do anything, you can move on. You're 90% sure we're good. So, now that we're done with that one, let's move on to number 19 and see what we can get here. Okay, so now it's going to fit into one of the ones we did earlier in the PowerPoint lecture. Show you the process. We have an x square root of x minus 2 dx. Now already I'm looking at this is I cannot distribute that x. I can't do anything here except I do have something that I can do where I can clean up the inside. Like I was saying earlier, a parenthesis inside of a root or a denominator or inside of a natural log, whatever. We'll get to those later. Generally, it's the inside of things that you want to replace with the u to make it a nice single term. So now my du is just 1. The derivative is 1, so du equals dx. And if you recall, this is one of these where that's going to become a u, that's going to be a du. And we have this problem right here with the x out front that didn't go away. Okay, sometimes we kill two birds with one stone where we take care of extra pieces and we take care of the du all at once. Sometimes like this, it doesn't happen that way. So what do? We have to do that little thing where we're going to take this right here and we're going to solve for x. So it's like I'm moving the 2 over. So x equals u plus 2. That's going to replace this right here. And remember, it's a parenthesis. Now, some of you may say, well, that didn't help much. But it does, because this is just a single u. That root is just a single term with a power. I can distribute that. Now, I didn't say it was going to look pretty, but it's going to be doable. This is what we get when we distribute. And as ugly as that might be, those two terms, you can integrate them. You have the procedure. So remember, this is u to the 5 halves, because I add 1 to it. Divide by 5 halves. This is 2u to the 3 halves. Divide it by 3 halves. And a plus 2. So our last part is move that fraction, reciprocate it so it gets multiplying, and then replace the u with our original x. And same thing over here. This is going to be a 2/3 times 2, so it's a 4/3. And that x minus 2 to the 3 halves. And last, sorry, by the way, this is a little typo. That's supposed to be a plus c back here. I don't know why I wrote it 2, but it's a plus c. Now, that whole big thing is what we have as our answer. That's what I need to type here into our problem. Now, this one, I don't know if I didn't do all this work for nothing, but it said, what's the appropriate substitution? Look at what we did. It's just the inside. It's not the whole root. It's just the inside there that we're going to do. So u is going to be this x minus 2. And check that. Uh-oh. Oh, did I click the wrong one? Sorry. Click C instead of B. There we go. And now, what is our indefinite integral? All of this we found. So it's going to be the 2/5 x minus 2 to the 5 halves plus 4/3 x minus 2 to the 3 halves plus c. Now, I'm going to admit to you right now, on problems like these, there's so much going on. It's very easy to mess up one little piece, especially, you may even have the right answer, like I think we have over here on the right, but if you type in something, you may mess one little thing up in the typing. So you got to be very careful, very meticulous, very slow when you're doing this. So watch out for a problem like this when you have these fractional powers. All right, so again, I'll pause if you need more time to look at this. Resume when you're ready. And let's see, we got all those? Yeah. Let's look at number 23. Okay, so we have another integral. Same kind of steps here. Just kind of writing this a little bit bigger so you can all see what's going on. Now, this one's a little tricky in the fact of, well, sometimes I want to get rid of this. Sometimes I want to get rid of this right here. And a lot of these, like I was telling you earlier, you'll know when you do it because the problem will tell you. As soon as you do the du, it's going to be very clear you're on the right track or you're going down an abyss here. So I'll kind of help you and tell you what it is. This is what I want to make better. When I see a power higher than 2, and I have a parenthesis with all these terms, I want to get rid of that. That's just too much extra steps, too complicated, too many terms, too many rooms for error. So I'm going to get rid of that. That's going to be the u. 5 plus e to the 3x. Okay, the entire parenthesis. Now, what's fun about this one is the du is e to the 3x dx. That happens to be the thing that I have right here and right here. So like I was saying earlier, you kind of kill 2 birds with 1 stone. This and this become the du. And that entire parenthesis becomes a u to the 4th. And look how easy you've made the problem. U to the 4th du. Well, that's u to the 5th over 5 plus c. And lastly, replace that with your original problem It's one of these that I will say looks worse than it is. I shouldn't speak too soon. Let's type it in and make sure we get it right before we declare such statements. And a lot of this you're going to learn on the homework. And take note of this, how to enter these problems, because sometimes we're going to have the powers in the wrong spot. We're going to have the parenthesis in the wrong spot. We have to make sure we enter these all correctly. I think we have it right here. All right, I did speak too soon. What did I get wrong? Okay, I think I see it. See if anybody noticed this. One major, could be minor, but it turned out to be major. Little error here. When I took this derivative, the derivative of e to the 3x, it is e to the 3x, but remember derivatives, we have to do the chain rule. I had to hit that with another 3. So du should have been 3e to the 3x dx. Okay, that's going to change our problem a little bit. How it's going to change it is we have to have a 3 in front of the ex. So we got to put a 3 here and a 1/3 there. And that's how it's going to affect my problem. So I'm doing this all kind of in the pink to show what it should be, so you can see the changes. And now my answer over here should be 1/15. Oh, let me erase that. 1/15. So I had everything right except that this should be, if I caught the correct error, should be a 15. And now we have it. So kind of make sure here what's going on. All right, you guys see what's going on? That's the derivative of this. The derivative of 5 is nothing. Derivative of e to the 3x is e to the 3x times 3, or 3e to the 3x dx. Okay? Now we have this, and we'll move on to the next one. Let's look at number 27. See what this is all about. All right. One of these, again, a lot of these, they look bad, but you have to kind of figure out what's going to make your life the easiest when you do a substitution. Okay, now I'm going to tell you a couple things. There's actually 2 answers here, 2 ways to do this. I'm going to pretend like I don't see a shortcut, and I'm just going to do this how we've been doing them all day. We have our substitution, our technique right here. Okay, so the process is, let's try to make something less complicated. Well, if you notice, and a lot of these is going to be from experience. I'm going to let the inside of that parenthesis be to the u. Now, a lot of times I only need to do this when it's more than one term. This is just one term, although it's a high power, it's one term. But I'm going to do it and show you what we get. Du is 11x to the 10th derivative dx. And what's great about this one, as you can see, it's the exact same thing as what we have right here and here. So my problem basically becomes u to the 10th du. All of this and this becomes the du. So I integrate e to the 11th over 11 plus c and substitute back. This is x to the 11th to the 11th over 11 plus c. Now, I'm going to type that in here just to see if it works. I have a feeling, see, it doesn't say to simplify. It should, but let's try this. X to the 11th, no, sorry. To the 11th over 11 plus c. All right, so it's right, but, and we're going to get the same answer no matter what, but let me just point out another way to do this. And they kind of eluded that. Substitution, we did it to find it, and then find it without using substitution. So I'm going to do that here, right down here. Now, what you notice is, this is something not as bad. Remember, a power to a power says we multiply powers. That's just x to the 110. And then a power, an x times an x, we add the powers. That becomes x to the 120. So I can actually integrate that where, let's go 1 power higher. divide it by the new power, 121 plus c. And then last, 11 over 121 becomes x to the 121 over 11 plus c. And I'll show you why these are good. Okay, so it's good, but look at this. Right here, our final answer, the last one, x to the 11th to the 11th is 11 times 11, it's x to the 121. These are the exact same thing. That's why I can type my yes here. Oh, sorry. And did I do it? There you go. We have our answer. So, like I was saying when I began this, U substitution is probably best when there's more than one term. But if you only have one term, you might be able to do it like I did here on the bottom right. But this is just showing you that it's going to work either way. Either way is going to work. In an actual test environment on your quiz, on your quiz next Monday, it won't matter. You can do either one of these methods and just do one of them to get your answer. All right, so let's look at number 31, I think, is our next one. Okay. So we have integral of r squared 7r plus 8 dr. Okay, find the indefinite integral and check the result by differentiating. And what that means is they just want you to find the derivative at the end to check to get your answer right. Now, two ways you can do this, but there's really only one way that's going to, I'll do them both ways. Let's just do our u substitution here. And we'll see how it goes. du equals 7 dr. Notice the derivative of 7r is just 7. So I need to put a 7 here. And I can as long as I balance and put one out front. Okay, so that'll give me the parenthesis is going to become a u. This is going to become my du. But I have this problem with the r squared. Okay, so how can I do that? Well, like we did before, remember, you can solve for r. You get u minus 8 over 7 equals r. That's what I'll tell you right now. Sorry, u minus 8 over 7. I'm going to tell you right now, this doesn't look like it made our life any better. Okay, because what I have now is I have multiple terms in a parenthesis to a power. I can do this if I wanted to, but this is going to get a little ugly. Okay, so let me show you the alternate here. Here's the original problem. We don't have to substitute at all. We can just distribute. And we get a 7r to the third plus 8r squared dr. And this is a simpler integration. Sorry, that should be a 3 on the bottom. And we don't have to worry about substituting back. That's our answer right there. That's all you need to do. So, point is, not always is integration going to be your best way. Sometimes it's going to make your life more difficult. So that's the part about let's always look and see what happens after you take the du. Maybe what happens after you do the substitution. Did I make the problem better or did I make it worse? If I seem like I made it worse, don't be afraid to just pause. Don't just erase it all. Let's just pause and see if we can do it another way, off to the side or another sheet of paper. Then if this didn't work, maybe you can come back and resume this one or kind of pick your poison, which one is best here. Okay, so again, pause if you need it. Resume when you're ready. And number 35, I think, is still in section 5.2. Yeah, we've got a handful here in this first half, the first section of your homework here. So this is going to be a little bit of a longer video. We have 10 over x natural log 3x dx. Okay, so now I got to figure out what I'm going to do here. And there's a couple of options. Now let me just write these and show you, but I'm not going to do this one because to find my du, I have to do the product rule. Now I know how to do that. If I have to, I will, but let's just wait a second. Let's try something else. Let me just do that. just get rid of the natural log part. So if I do that, well, the derivative of natural log, remember, is 1 over 3x, and then chain rule times 3 dx. du is 1 over x dx. What's great about that is, let me do a little rewrite of this problem. I could put the 10 out front. I have a 1 over x natural log 3x dx. And you don't have to do this rewriting, but I just want to show you what I have. This is the same exact thing right here. And now maybe it's a little more clear that, okay, here's the 1x and the dx, just like I have right there. Those two things combined become the du, and then everything else just replaces like we were expected. This is going to be a 1 over u. Okay, so I've done the substitution. I figured it all out. I'm going to go over here to the left. I have a 10 natural log of u plus c. That's the integral of 1 over u. It is natural log of u. We knew that. And then last, substitute back, and that's natural log of 3x plus c. So it's a little tight, but there's our answer. And yes, as you can see on this example, it's okay. You can have a natural log or a log inside of another log there. Okay, so we end up with 10 natural log of 3x plus c. And there's our answer to that one. So a little bit weird, but it's follow the procedure and it will get you the answer. All right, and I think we have one more before we get to section 5.3. Let's look at number 39 here. One of these word problems, just because I know they slip a few in here, so let's make sure you know how to do these. All right, we have w prime of t equals 0.2 e to the 0.1 t. Now they ask you if the starting culture weighs 2 grams, what will be the weight of the culture? WT after t hours. This is the first question they're looking for, and you can see it right here. All right, how do we get it? We're going to take the integral of this. And I will do a u substitution just because I want to get that power a little cleaner. So du equals 0.1 dt. Okay, so what that means is I need to have a 0.1 touching this dt, multiplying. I'm putting it on top, but it's multiplying. So let me just rewrite this a little nicer so you can see where I'm going. Going to be multiplied times a 0.1, and the dt is still there from above, or because we're doing the integral. So this right here is going to become my du. And then the 0.2 I can put in front or I can leave it there, it doesn't matter, but this all becomes e to the u, because remember this is what I let the u be equal to. So now my answer is simply 0.2 e to the u plus c. Not done yet. And then we have to substitute, which says the thing we're finding is w of t. All right, so that's what we just did because we did the integral. It's 0.2 e to the 0.1 t plus c. All I did right there was I substituted back the u. Okay, now we have our answer in terms of t. Now, the question is, what's w of t? Well, we have it except this mystery c. And you recall our last example in the PowerPoint was we're going to use this information right here. If the starting culture weighs 2 grams, so we have to kind of look at what's going on here is, this is how fast it's growing. What will be the weight of the culture? So W of t is the weight, t is the hours. So what they're saying is it started at 2 grams. And it starts at 2 grams when t is 0. That's what it means when it's the start. So it's like I'm finding W of 0. Put a 0 right in here. Plus c, and then of course the whole function, the weight equals 2, and that's what we're going to find. So e to the 0 is what I have here. E to the 0 is 1, so this is all we have is 0.2 plus c, and then subtract it, and I think we get a 1.8 equals c. So now I can go and rewrite that original equation to be 0.2 e to the 0.1 t plus 1.8. That's my W of t formula. After all that, that's what I found it to be. So now, of course, the hard part, if we got it right, and we need to type this in correctly, e to the power of 0.1 t plus 1.8. Okay, what did I do wrong here? Okay, I started doing it, but I got caught up because I rewrote the problem. Remember, we put the 0.1 here. We had to put the divided by 0.1 out front. Okay? Important little steps. So what I'm going to do is I'm just going to do the problem over from this point right here. Let's get rid of everything that we've done. Won't be too hard. But you see that one little mistake does change the entire problem. And it's not like it's, like I said, it's not a major mistake, but it's going to look bad when you look at the entire problem. If you look at the actual answer, I'm going to be way off on this one. Okay, so I'll show you how to proceed from the error. Everyone see again what happened was I multiplied by a 0.1 to get the du correct, but I had to divide by a 0.1 to make it there. So when we do that, this 0.2 comes out and is divided by the 0.1, which essentially is a 2. So that's our problem. It's actually going to be a little easier in this step. So W of t equals 2e, and I'll replace the u with the 0.1 t plus c. Okay, so there's our function, starting function. And we need to go do the same part again. They told you the weight of the culture after t hours. It started at 2 grams. So we're trying to find W of 0, and that is 2. So 2 equals 2.1 times 0 plus c. 2 equals 2 plus c. C equals 0. So this is my answer right here. It's just going to be 2 e to the 1.1 t, and there it is. Okay, and then the last part, what's it going to weigh after 6 hours? So I have to go plug in W of 6 to this answer right here. The actual function, the one that's right above it right there. And that's going to be 2e to the 0.1 times 6. So I have to go figure this out. This will be a calculator, and they say round to the nearest 100. I have my calculator here somewhere. There it is. So I just got to punch all this in. I have to find out, if you can't do this in your head, go ahead and work it out. 0.1 times 6 gives you a 0.6. That's going to be my power of e, and I multiply that by 2. And we get 3.644 all this. They want this to be to the nearest hundredth. So 3.64. And there's our answer. Okay, so check that one out. Let me slide this back up just to kind of see where we were. And now, I think that's going to be it for section 5.2. Yeah, now we're hitting 5.3 stuff. Let me get rid of this and kind of show you where we are. We've gone all the way up to here, so it's probably about 60-70% of your homework you should be able to do with this first lecture. I'll record one for section 5.3 and post that shortly. Again, until then, if you have any questions, let me know, and have a good night.